Hello, 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 hello.
Your Lord and Master is kicking out, kicking out, kicking out, kicking out. I don't know his name. His master's voice. You should have your own cooking on the television. Roughing. Won't be long, old fatty oven. Buzz off. Oh, sniff that.
Are you thinking about go on?
Oh, no, sir. Great, futters. Tough as a boy would.
I wouldn't do that. Worms. Don't even think about it. Oi, you stop. Look at that.
We've left the trap door.
What of it?
Two things it might be a good idea.
Is it? Glove it. Aha! Mirror.
Well, on reflection, I think that worked well. I must say, he was an ugly brute.
Where's my breakfast?
Inside the big yellow thing, your Come on. Oh, talk about fast food. Here you go. Chef, come on.
Well, on reflection, I think that worked quite well. Reflection, I think that worked quite well. On reflection, I think that worked quite well. I think that worked quite well. I think that worked quite well. Worked quite well. I think that 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 worked quite well.
Overworked servant of the thing upstairs.
Feed me.
But that's nothing compared to the horrors that lurk beneath the trapdoor. For there is always something down there, in the dark, waiting to come out.
Meow.
dark and nasty regions where nobody goes, stands naked and cast. Deep within this dank and uninviting place lives Burke, overworked servant to the thing upstairs. But that's nothing compared to the horrors with the back door, for there is always something there in the dark, waiting to come out. Overworked servant to the thing upstairs. But that's nothing compared to the horrors that lurk beneath the trap door. For there is always something down there in the dark, waiting to come out. stands an ancient castle. Deep within this dank and uninviting place lives Burke.
Hello.
Overworked servant of the thing upstairs.
On a spring will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed of the disc. If we set the weight oscillating in time with the spot on the disc, the weight is always at the same horizontal level as the spot. Horizontal level as the spot.
This rotating disc and this pendulum will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed. If we start the pendulum swinging just as the spot passes the pendulum stays in a vertical line with the spot.
The vertical locations of both pucks are examples of simple harmonic motion. All three pucks exhibit simple harmonic motion in the vertical direction.
These two spheres on the edge of a disc rotate with the same period. We'll backlight the spheres so that their motion appears one-dimensional and simulates simple harmonic motion. We can change the relative phase of the spheres by moving them to different parts of the disc. Here the spheres are moving in phase. Here they are moving with a phase difference of 45 degrees. Here is a phase difference of 90 degrees. 135 degrees. 180 degrees.
'" The motion of this heavy pendulum bob can be described by a sinusoidal function of time. This special type of motion is known as simple harmonic motion. The motion of the flexible wire at the top cannot be described by a sine function. It is not simple harmonic motion.
We'll use this glider floating on a cushion of air and these springs to investigate simple harmonic motion. If a spring is attached to each end of a glider, the glider will oscillate back and forth on the track. What will happen to the period of oscillation if we double the mass of the glider? The top half of the screen shows the original arrangement, while the bottom half shows the glider with twice the mass. The period has increased. What will happen to the period if we add another spring to each end of the glider instead of more mass? The top half of the screen now shows the original setup, while the bottom half shows the glider with another set of springs attached. The period has now decreased.
Now, quantum mechanics is not theory, but we have to appeal to experiment to see what theory will have.
Here are some tracks produced by particles like electrons and protons in a device called a bubble chamber. They're certainly suggestive of tiny particles following definite paths as they fly across the chamber. And you can also probably see that they're bent around. That's because the whole chamber is in a magnetic field. And if I measure the curvature, I can use the laws of classical physics to work out the momentum of each particle. In fact, you've used just this idea in a summer school experiment, the magnetic field experiment. This is the apparatus you used. And if I turn on the magnetic field, you can see the electron beam being bent just like the particles in the bubble chamber. Well, so far, there's nothing to suggest that the laws of classical physics can't handle all this. But take a look at this apparatus over here. Here's a similar sort of tube with an electron gun, and the electron beam hits the phosphorescent screen here at that spot. And I can move it around with a magnetic field from this tiny bar magnet. But now suppose I were to put this very small metal foil in that tube just downstream of the electron gun. Now, what effect do you think that would have? Well, I can actually do that experiment, because over here I have a tube with just such a foil installed in it. So let's dim the studio lights, and I'll turn up the voltage on the electron gun. I'll do it just once again. And there you can see this beautiful ring pattern, undeniably a diffraction pattern. But these are being produced by electrons. Yet I can only explain that in terms of a wave phenomenon. In fact, if I measured the position of those rings, and I knew the spacing of the atoms, I'd be able to use the diffraction formula to actually work out the wavelength of the electrons. But what does it mean, wavelength of an electron? After all, a moment ago, I was talking about them in terms of particles. And those particle properties haven't gone away. If I were to turn down the intensity of the electron gun, you'd find that individual electrons leave the gun, and individual electrons arrive in different parts of the ring pattern. It's just that the intensity is so large that normally the huge number of electrons evenly illuminate the rings. But now our classical physics really is in trouble. It can handle things like particles, or behavior like particles. It can handle behavior like waves. But it's in difficulty explaining what happens with electrons behaving like waves and particles. So where do we go from here? Well, maybe we should look at the connection between the momentum and the wavelength of an electron.
The electron's wavelength is given by this formula, which was first written down by Louis de Broglie. It says that the electron's wavelength, lambda dB, is equal to h divided by the magnitude p of the electron's momentum. The constant h is, of course, just Planck's constant. It's a constant that crops up in practically every equation in quantum physics, although it never occurs in classical physics. Well, there's an important point to remember about this equation. It applies not only to electrons, it applies to any particle with momentum p.
Well, here's a moving billiard ball. It's certainly got momentum. Let me apply de Broglie's formula to it. Maybe it's got an associated wavelength, in which case I should be able to diffract it, just like electrons. And here, in fact, is a diffraction grating, regularly spaced slits about 20 centimeters apart. So let me fire this billiard ball along the center and see what happens. Well, just as you'd expect, I think, they went straight down the middle. Quite different, though, from our electrons. Remember how they diffracted in our earlier experiment with the tube. Well, why didn't I get diffraction effects with billiard balls if they have an equivalent wavelength? Why didn't they arrive on either side of the pocket, giving the usual pattern of maxima and minima? Maybe we should put the numbers into the de Broglie formula. Well, what's the mass of a billiard ball? Say 4 ounces, about 100 grams. So I have m equals 0.1 kilogram. And if I say the speed is about 10 meters per second, v equals 10 meters per second, then I can work out the momentum, and it comes out to be 1 kilogram meter second minus 1. Now let's use the de Broglie formula, lambda equals h over p, to work out the equivalent wavelength. Well, if I put in the numbers, because h is such a very, very small number, then lambda works out to be 10 to the minus 34 meters. Now that's an incredibly small wavelength. Let's see what the equivalent diffraction angle is. This is the formula I need for diffraction. Lambda equals d sine theta. Remember that d is the slit spacing and theta is the angle of diffraction. Here's the first order diffraction here. Well, again, if I put in the numbers, I'll find that theta is about 10 to the minus 33 radians. Well, that's a fantastically small angle. And what that means is that these various orders of diffraction all get squeezed into an infinitesimally small area around the axis. So small that we'd never ever be able to observe them. And the important conclusion is that these everyday effects don't actually contradict the de Broglie formula. It's just that for the everyday world, we don't have to be concerned with wavelengths of objects like billiard balls at all.
But we do observe wave-like effects with electrons. As John showed us, they're diffracted. And when we do experiments like this, we find that the wavelength of an electron is given by the de Broglie formula. Well, electron diffraction is a purely quantum effect. We can't explain it using classical physics. So now let's move on to look at another way in which classical physics and quantum physics part company. When billiard balls are set up like this, I know that if a ball comes in from this direction and hits the blue just tucked in behind the yellow, then both of these reds will be pocketed. Well, it wasn't just because I've seen it before. The result's entirely predictable on the basis of classical mechanics. If I came back next week and played the same shot, we'd get exactly the same result. Well, this idea of predictability is really just common sense, and it's completely basic in classical physics. If you do an experiment and get a result, then if you come back later and do the same experiment,